Okay, we'll now start Chapter 10. Chapter 10 deals with two sample inferences. We got two sample intervals and two sample tests. So, and we've got the proportions and means. So there's a total of 4 inferences that we're going to make. But first of all, some theory behind this chapter that we've looked at before. And the concept of a sampling distribution is going to be an important thing to establish the theory of what's going on. So what we've done up until now is we've done one sample stuff, and all of the terminology that goes with this is very important. And so in other words, we've got some population that we're interested in knowing something about. So let's say the population is let's say every student that goes to Grissom High School, and we have something we're estimating. Maybe it's a proportion, okay, like the proportion of students that are going to end up going to college, or who are planning on going to college. And so we could take a census and find that number, and that number is what we call a population parameter. Parameter describes everything in the population, but what we decide to do is we decide to take a sample. Let's just pretend a sample of, 100 students or something, and we find a p hat, a proportion in that sample that are going to college, and this is what we call a sample statistic, and it estimates that, and we would use this sample statistic to create a confidence interval. We would go a little to the left and a little to the right, and we would say, hey, we're reasonably confident that P, the proportion of all Grissom students that say they're going to college, is in this interval, and so forth. And we did the same with means, maybe a mean test score on some standardized test that we're estimating. Mu is the parameter. It describes the whole population. Let's say if our big N, our population size, is 1,800 students, okay? And so we could take a census and find mu. But we decide to get a sample statistic, X bar, to estimate that, okay? So, let's say our sample size was, let's say, 50 or whatever. And so these are our statistics, okay? These are our parameters. Those are important concepts. That terminology. And of course, with this X bar, we would, just like with the p hat, we'd make intervals with it, we'd do hypothesis tests with it, and so forth. And so that was, basically what we did in Chapter 7, 8, and 9. But now what we're doing, it's not so much one sample, we're going to go 2 samples. We're going to go, we're going to have one population, we're going to have another population. And we are interested in comparing these 2 populations. So this P could be, the proportion of people that take a drug that get better, they have some disease. And then P sub 2 may be the proportion that take a placebo. And so that's very interesting to us to see whether or not things work. Well, if you're going to figure out whether or not things work, you need to compare them to something else. So this could be the proportion of students who pass a test who went through a computer program. And this is the proportion of students who passed the test that did not go through the computer program. And so we're comparing 2 things in essence. And so the same thing with the mu. This could be the mean test score, of the students that went through the computer program. We call that mu sub 1. And so this would be p hat sub 1, x bar sub 1. And then our mu sub 2. Our second population would be the students who did not go through the computer program. And of course, we would estimate this with an x bar sub 2. Okay, so in essence, we've got 2 populations in every one of these problems in this chapter. The population of, let's say this is students at Grissom High School and this is students at Huntsville High School. And we're comparing the proportions that are going to end up going to college. And so we would get a p hat sub 1 and p hat sub 2, and we're interested in the difference in those 2 numbers. And so we're going to create a confidence interval for the difference. But the terminology of there's, the parameter here, there's the statistic, parameter, and statistic. And so we're going to do, so what we'll do is we'll subtract these 2 sample values and as an estimate for the true difference. And do the same thing here. We'll subtract these 2 sample values. And we're interested in the difference, in the people that went through the treatment and those that didn't, or the difference in the weights of the tomatoes that got the fertilizer and those that didn't. And so we're going to subtract these 2 numbers. And with these 2 things, with these 2 differences, we're going to make an interval around them, and we're going to do hypothesis tests with them. And so I've got 2 main contexts right here in the 10-1 in the 10-1 examples, and some of this can be a bit confusing, but here we go. And so the first thing we're really going to talk about is the concept of a sampling distribution and how relevant that is, and then we'll go on and we'll do our two-proportion Z test, two-proportion Z interval, two-proportion Z test. All right, so here we go. So it says a forest ranger wishes to know the difference in something, the difference in the proportion of oak trees in his forest that have a particular parasite and the proportion of pine trees in the forest that have a parasite. Unbeknownst to him, 40% of the oak trees have the parasite and 32% of the pine trees have the parasite. He takes an SRS of 200 oak trees and another SRS of 200 pine trees. He finds the proportion of each that have the parasite and finds the difference in the proportion. Describe the sampling distribution. So what we've got here is we've got two populations. We've got a population of oak trees, and then we've got the population of pine trees. So we've got two populations, and so that leads us to believe, hey, this is a Chapter 10 problem because we've got two populations, and we've got two separate samples from those populations. All right, and so what it says here, it says, unbeknownst to him, 40% of the oak trees have a parasite, okay? And so that is going to be 0.4. That is a parameter. It is not a p-hat. It is not the sample proportion. It is the parameter. So I'll call that P sub O for oak, all right? Or you could call it like P sub 1, all right? And I'll call P sub P, it says 32% of them. So that is, in essence, the parameter. So it asks us to describe the sampling distribution of the difference. Okay, so now we understand, since we know the proportion, the difference is going to be 0.08, but we're estimating that with sample values. And so what's happening here is this. In Chapter 7, we learned about the sampling distribution for one sample. So with the oak trees, we take a sample of size 200, okay, and we get a p-hat. It's probably not going to be 40%. It's going to probably be somewhere around it, but just because of sampling variability, it'll be somewhere off from that. And whenever we get a sample statistic, a proportion, we know it's one of many we could have gotten. If we took another sample of size 200, we would get another p-hat. And if we took a third sample of size 200, we get another p-hat, and so forth. And this family of p-hats, every possible value p-hat could take, is what we call a sampling distribution. And it will be approximately normal because our n times p and n times 1 minus p are clearly bigger than 10. All right, so it is approximately normal. It'll be centered around 0.4. Okay, in general, be close there. Most of them will be around 0.4. And then our standard deviation of this, of our p-hat sub aught, in essence, is the square root of 0.4 times 0.6 over 200. And so that is how we did it with that distribution. That's what we did in Chapter 7. Then we do the same thing with the pine trees. So with the pine trees, we would realize, well, if we take a sample of these pine trees and we measure the proportion that have this parasite, it's probably going to be around right near 0.32. Because that's what the population proportion is. But it's going to vary from that almost certainly because of sampling variability. And if we took another sample, and if we many samples and got many different p-hats, it would create a sampling distribution. Every possible value a statistic could take. And once again, it's going to be approximately normal because of our normality policy there, which is p times 1 minus p, and this also are greater than 10, or n times p and n times 1 minus p are greater than or equal to 10. So we get this. And so they are going to be centered around that. And in the standard deviation of these p-hats, the average amount of these p-hats vary from the middle. So the standard deviation of these p-hats, and I'm calling these p-hats sub p, it's the p-hats that deal with the pine trees, that's going to be the square root of, that's going to be 0.32 times 0.1 minus that, which would be 0.68 over 200. Okay? That is equal to like about 0.033 approximately. This is like 0.035, a little bit more. But what it's asking us about is this. What we're interested in is the difference in these two things. We're going to, in essence, subtract these two curves. We're going to find a p-hat here, one of these. We're going to find a p-hat here and subtract them. And in general, like I said, we're expecting it to be, somewhere around 0.08 because that's the difference in the population values. But it's going to vary from that. I may very well get like 0.42 here and may get like 0.34 there or something like that, or let's say it's different, like 0.33. And be a difference of 0.09. It's probably going to vary from that. So what's happening here is this. I'm interested in this random variable like we talked about in chapter 6 of oak minus pine. And so what's happening is when I subtract these things, now the true difference is 0.08. Okay, but each individual one is going to vary around that. I may get like a 0.4 here, and then here get a 0.33. And so that would be a difference. I'll call that little d for difference. And so that would be like 0.07. Or I may get 0.39 here, and let's say 0.30 here. And so that would be 0.09, and so forth. And if I did this many times, I kept subtracting these values, they would vary, these differences. And they would create what is known as a sampling distribution. This sampling distribution will be approximately normal because when you subtract two normal curves, the result is a normal curve, as we talked about in chapter 7. The mean of these differences, as we call them, is going to be 0.08. Okay? Then now, what about the standard deviation of these differences? Okay, you may recall whenever you combine curves, random variables, okay, you can, like let's say you subtracted these two things, you can subtract the means, but you remember we always have to add the variances, okay? And which is the square of the standard deviation. So hopefully you remember back in chapter 7, you can go watch the videos in regards to that if you want to brush up on that. But whenever you subtract random variables to find the standard deviation, you have to add the variances. And so we'll find the variance, the square of the standard deviation first by just adding these two. So that's going to be 0.4 times 0.6 over 200, and then plus that, you add the variance here, which is the square of that. In other words, I just leave the square root sign off. 0.32 times 0.68 over 200. And that, in fact, is going to give us the variance. Well, I'll just take the square root of both sides here. If I take the square root of both sides, let me get rid of that squared, and we have ourselves the standard deviation. And that, in fact, is the theory behind this formula. So in our formula sheet, we made it almost to the bottom of the last formula sheet, but the standard deviation of the statistic that we're going to use, this is what we just did in chapter 9. Now in chapter 10, it's this. I mean, it looks really complicated, but that is, in essence, what we just created. So if you don't understand what I just did, you can just look on the formula sheet. And so that is, in essence, the origin of that formula. And that's why we did all that stuff with random variables, by the way. And so this number ends up being, if you were to calculate that out, I do believe 0.047833. So 0.047833. So all that being said, how would you describe the sampling distribution? Well, how would you describe any distribution? You cuss, remember from chapter 1? All this, you'd say, describe the center. Well, the center of the differences is going to be, 0.08. Okay, there you go. That describes the center. And then the shape is going to be approximately normal. Okay, and by saying approximately normal, that takes care of the unusual values too, because by saying approximately normal, it tells you the nature of the outliers. And then lastly, the spread is described by the standard deviation of 0.047883. And so that is the sampling distribution, and that is the theory behind how we're going to do our mechanics when we do our interval in our test. It's just how are these differences, in essence, varying. Anyway. Okay, by the way, the notation for this that you'll see, I kind of like using this notation. The notation they use for this is the standard deviation, and the differences are going to be they're going to put this notation down. It's going to be p hat sub oak minus p hat sub p. And so, I mean, to me, that's just easier. But that is typically what you'll see for the standard deviation of a sampling distribution of p-hats. Okay, now let's go ahead and let's look at our main context for this section. And we are going to do, so in section 10.1, it is a 2 proportion z interval and a 2 proportion z test. Those two things. And section 10.2 is going to be a 2 sample t-test for a difference in means. And in a 2 sample t interval for a difference in means. So, okay, so let's look at this situation here. Sandy wishes to see if there's a significant difference in the proportion. So you notice difference in proportion. So that's telling you the fact that they're dealing with a difference, that is a good chance you're saying chapter 10. Okay, and proportion means 10-1. Okay, so we're dealing with all this proportion stuff. The proportion of boys at her school who like the school lunch and the proportion of girls at a school like the school lunch. So that seems like two different populations that we're studying here. All the boys at the school and all the girls at the school. All right, and then in the parameter is going to be the proportion of each that like the school lunch. So that's how we're sort of defining a success in this situation. Takes an SRS of 100 boys and finds that 56 of them like the school lunch. It takes an SRS of 100 girls and finds 45 of them like the school lunch. So let's write that down. So we have our P hat, I'll call this P hat sub B for boys, and we have 56 out of 100. 56 out of 100, or 56%. And then we have our P hat sub girls that we're comparing that to. It's 45 out of 100. Okay, certainly in the sample, more boys like the school lunch. But what we're saying, what we're going to do is we understand these are estimate values. These aren't censuses. This is estimates. And so we want to make an interval for the difference. And then we're going to test to see, is this a significant difference? And that's sort of the big deal in this chapter. We understand these things are different, but are they significantly different? In other words, are they so different that we would rarely expect it to happen by sampling variability? So here we go. It says create a 95% confidence interval for the difference in the proportions of the boys and girls that like the school lunch. And so, of course, it's an interval, so we're going to make the TAME acronym, just like in essence we did in Chapter 8. And so here we go. And so the type of inference. And so, and at this point we're starting to accumulate several of these things. But the type of inference, this is a two-proportion Z interval that we're going to make. Once again, you have to say four things. You got to say, is it one or two samples, which two? Is it a proportion or a mean? Is it Z or is it T? And is it an interval or a test? You've got to say all four of those things. And so there we go. And so that's, if you can do that, that's 1/4 of the problem you've gotten right. Our assumptions are very similar. Okay. Each time we do a different test or interval, we have in essence our SYN acronym, but we're going to modify it. Every one of them's a little bit different. Now it's ISYN, which is a little bit different. ISYN. It's not just a simple random sample. It is an independent. We're having two aspects of the word independence when we have our two sample stuff. It has to be an independent random sample is what it has to be. So in other words, they had to have been taken separately, and there was no pairing going on, like in a matched paired situation, which we're going to practice, more later in the chapter. So they had to have been done separately. They couldn't have been influencing each other in any way. And so this is the way, in essence, I want you to word this. So independent random. So it needs to say, as we talked about, it needs to say either SRS or random sample, or random assignment to treatments in an experiment, which we're going to do an example like that in the next video. But and so we would say this: it says SRSs, there's two of them. We got two populations. Don't just say SRS. SRS is two of them. It says SRSs were taken, thus independent random condition is met. A couple years ago, I had to grade one of these, and if you did not say independent random, you got at best A partially correct for all of your assumptions. You have to say independent random samples if it's a two-sample situation. And definitely less than half of the people did that. There's most everybody would say random, but you have to say independent random right there, not just independent here. And so that is the first thing. It's the ISIN, okay, ISIN with the two sample. And of course, this is the other aspect of the word independence. The other aspect of the word independence are population sizes. There's two of them, okay, have to be greater than or equal to 10 times our sample sizes. Okay, so there's 100 boys in the sample, so you're going to say this: there must be at least 1,000 boys, and then have to have 1,000 girls, and 1,000 girls at this school for our population sizes to be greater than or equal to 10 times our sample sizes. And that's considered standard notation for population size and sample size. So to me, that's the quickest way of saying it and getting full credit. So there we go. And then we have normality. So we have normality. Okay. Now the thing about, it's still going to be our old rule with proportions. N times P and N times 1 minus P are greater than 10. But the thing about it is we've got two samples here. Okay, so we've got to do it twice, one for each sample. So this is, and I'm calling this N sub B. So N sub B for boys, and then P, and then, so I'll put the B's down for the boy sample, and then the same with the girls. The girls, N sub G times P, and N times 1 minus P, and I'm putting a little subscript of a G for the girls. And so this is in essence, N sub P, and so this is going to be, 0.56 times 100. This is in essence your number of successes for boys is what it is. And so it's going to be 56. There's 56 that say they like the school lunch, which that means there's 44 that don't. This is your number of successes for the girls, which is 45. And then that's the number of failures for girls, which is going to be 55. They're all greater than or equal to 10, so you can say thus normality is met. Thus normality is met. And that's the easiest way to say it. The longer way of saying it, which I used to require, is because these are bigger than 10, the sampling distribution of every possible difference is going to be approximately normal. Every p hat sub b minus p hat sub g, when you take all of them, we took many, many different samples, and you subtracted the proportion every time, every possible difference varies approximately normally. But the easier way of saying it is just to say, thus normality is met. So this is a little more complicated than the regular sinning we've done in the past couple of chapters, but it's not too much more. Just remember, independent random sample, and you have to check the greater than 10 for all. And all four of these, by the way, have to be bigger than 10. If any one of them is less than 10, then normality is not met. Okay? So now let's go on, and we go to the M, to the mechanics of our interval. So we go tame, we've done the T type, and then we've done the A for the assumptions, otherwise the condition, and our mechanics. Mechanics means we're going to write our interval. Now, okay, I'm going to show you the formula for this. Yes, just like in Chapter 8, you can use your calculator and find the interval, okay? And, the formula is, it is a bit complicated, but yes, you do need to understand how to use the formula, but in general, you can use your calculator to find the interval. Well, let's look at our formula sheet, okay? Every confidence interval is statistic plus or minus critical value times the standard deviation of the statistic. Well, here our statistic is actually going to be we got two of them, and we're subtracting them. The critical value is Z star, just like it was in Chapter 8, and then the standard deviation of the statistic. Well, let's look down here at our table. So that's when we were dealing with sample means, so that's going to be in Section 10.2. And so there it is, difference in sample proportions. There, and I mean, it's not hard, it's tedious. It's, but they wrote you the formula there. So anyway, so let's write in essence our little formula down. And so what it is going to be, our statistic is actually the difference in statistics, which is our x bars. We subtract our x bars for our boys. I'm sorry, I just went to a section ahead. We're not in x bar, we're in p hats. Sorry. Don't make that error, please. Anyway, all right, so it's going to be our p hat sub boys minus our p hat sub girls. That is our statistic. We're subtracting them. Plus or minus our critical value is our z star, which we can get off a table or use inverse norm on our calculator to get. The square root of, all right, and it's going to be p hat times boys times 1 minus p hat for our boys over the sample size for our boys. And then plus the same with the girls. We take our girls' p hat and then 1 minus that, like that, and then the sample size for our girls. So there we go. And so that is the standard error. This thing right here. That's, if you're asked what's the standard error, it's that. There's a critical value. That's our margin of error. Every margin of error is critical value times standard error. That, of course, this is our point estimate, this difference. So that's the terminology there. And so if you were to plug now, if you're asked to show your work, it's, don't worry about showing the formula because like this, but show it with the numbers. Because if you show it with the letters and you mess something up, then you're going to get counted wrong for it. Like very typically people forget to put the hats on their P's. That's not good. So anyway, and so when you subtract, so remember our p hat sub boys is 0.56, and our p hat sub girls is 0.45. It is 0.45. So our p hat sub girls is equal to 0.45. So we'll enter all this in, and so this minus that, so that's 0.11. All right, our z star. Well, let's get that. Remember, go to your table B. Remember, go to your table B, which has your critical values, and you would just go to. We'll make ask for a 95% confidence interval, so it's 1.96. Hopefully, maybe you've realize that for now, or you could do inverse norm of 0.975. That would generate the in essence the same thing. If you were to go like this and you were to say, okay, so second distribution and go to inverse norm of 0.975 because you have 2.5% on each tail. I'm not going to go into that thoroughly, and it would give you a more exact value if you wanted the more exact value. I added on the 0.025 because there's 0.025 in each tail and 95% in the middle. But anyway, I don't want to start rambling too much, but this is about 1.96, and this would be the square root of, and we did enter those numbers, 0.56 times 0.44 over our sample size is 100 for each of them. Yes, 100 for each of them. And so this is 100 plus, and then that's 0.45. And then times 0.55 over 100. And so this is 0.11 plus or minus. When you multiply all that out, I do believe you get 0.1377. I think your standard error here, this term, is 0.0703 approximately, if you find all of that. And so you get that. And so thus our interval is going to be negative 0.0277 to 0.2477. Now I did this. I found this interval using my calculator, which is a more exact value, by the way. So it's, sometimes because of rounding can occur, and you got to be careful when you're entering in your calculator. But anyway, so that would be considered fully showing your work, and you don't have to write that. If you were asked to show your work, then you could just show this. Just show these two lines, and that would be considered showing your work. But writing you don't have to worry about writing the letters. And so, okay, so there's our interval. Now and of course, we're going to say we're 95% confident that this interval captures the true population difference. Okay, but let me just show you quickly with your calculator function how you would do this. So we're going to go to stat, and we're going to go to test. And we are going to go down to a 2 proportion z interval. So you need to practice this enough to where, because we're starting to accumulate a lot of these things. We're going to have 4 more this chapter. We had 2 in chapter 8, 2 in chapter 9. So that'd be a total of 8 functions that we've learned by now. So 2 proportion z interval. So don't get these mixed up. And so we have, you can tell I've practiced this. So this is 56 out of 100. So remember, these have to be integers. You can't put 0.56 there. That X is your number of successes. And so it's 56 out of 100. Frequently in this problem, they won't give you the X, they'll give you the p hat. And if they do that, multiply it by the n to find your x. They have to be integers. And then there's my confidence level of 95%. And so I go, and so there we go. And so there's my confidence interval. And of course, this doesn't have units, it's a proportion. And so then to end this thing is our ending. So in other words, to state our conclusion or to interpret our interval, you would say this. You would say this interval, just like what we did in Chapter 8, this interval, and say what it is. So negative 0.0277 to 0.2477. Okay. I'm sorry. I am 95% confident. I should say that first. I'm 95% confident that, I got ahead of myself, that this interval captures what? Captures the true difference in the population proportions. So captures the true difference of the proportions of the boys and girls at this school, that like the school lunch. I realize that is a bit cumbersome, but the whole premise of this is this is an estimate for the proportion of all the boys. That's an estimate proportion of all the girls, and we found the difference, and we are 95% confident that the true difference is in essence in there. And of course, one of the things that's going to be most interesting to us is in this chapter, and this is going to be asked a lot about, because it's asked a lot about in the exam, what is in this interval? And in this case, 0. Because 0 is in this interval, there's plausibly no difference between the boys and the girls. In other words, there's a difference in the sample proportion, but it's not statistically significant. And this will get borne out in the test. So, okay, that's it. That's how you do a confidence interval with a difference in proportions. Now, number 2 says this. It says, perform a test of significance to see if there's a significant difference between the proportion of boys and the girls that like the school lunch. Well, like I just said, all right, one way of doing that is to do what we just did, to make an interval and say whether or not 0's in there. Because, we're going to do a two-sided test here, but our way of doing a hypothesis test is to find a test statistic p-value. And so that is what we're going to do. Now, we're asked to do a test, so whenever you're asked to do a test, the THAME acronym. This is really similar, but make sure you're, to what we've done before in Chapter 9. Make sure you're cool with the differences here. The T's, you always state your type of inference. Technically, if you write the formula, it's considered naming the inference, but I really don't like to write the formula because it's sort of complicated. It's easy to make a mistake and to get it wrong. So, and you can get docked for not doing proper mechanics and for properly naming it then. So I just like memorizing the type of, I like for you to memorize the type of inference. This is a two-proportion Z test. There we go, two-proportion Z test. And so here we go. So that's 1/5. You get 1/5 of it right if you can say that. Now, of course, we have hypotheses. Our null hypothesis is always going to be that our two parameters are equal, is that the proportion of the boys that like the school lunch is equal to the proportion of the girls. So you're always going to have that just these two proportions are equal. Never put a p hat here or never put an x bar. In the next section, this is going to be a mu, but right now it's a p, okay? So our alternative is what you suspect might be true. So the null is always no change, no difference, or status quo. We assume that they're the same. The alternative is what we suspect. In nowhere in here did it say we suspect that the boys is more than the girls or anything like that. It just gave the sample values, and it's not considered ethical to look at the sample values to determine your alternative. It has to be something that is done before that. And so in that case, you go with the two-sided, not equal to, like that. Okay? Now, and of course, we're going to have to find, anytime you write a anytime you write a letter like this, you got to define what it is. But also, let me say this to you. All right, the other way this is written could be this. You could write this like this. You could, like if I subtract P sub G from both of these, you could say P sub B minus P sub G is equal to 0. So that and that are saying the same thing. And so over here, this could be written as that P sub B minus P sub G is not equal to 0. So that is the same thing. In our book, a lot of times we'll do it like that. So they're sort of the same thing. They're both saying the null is that there's no difference, and the alternative is that there is a difference. Okay. Now, this is a bit cumbersome, I know, but you have to define your variables. You have to say, what is P sub B? P sub B is the proportion of all the boys at the school that like the school lunch. You have to define it. Make it clear that it's all the boys, not just the 100 in the sample. It is all the boys. This is a parameter. And then P sub G, and I like for you to use ditto marks. That actually makes it easier for me to read. P sub G is the same thing for the girls. So just go ditto mark, ditto mark, ditto mark, ditto mark. So all the girls. And to me, that's easier to read than writing it all out. But there we go. And so I've defined my two parameters. Okay, our assumptions are the same as on the other side. So I'm not going to write them out again. It's still same, as, with interval. So I'm not going to write all those out again. It's I sin. Has to be independent random samples. And then our population size is at least 10 times our sample sizes. And then n times p and n times 1 minus p for both samples have to be bigger than 10. So same as with the intervals. All right, our mechanics. And so now we got to get our test statistic. So test statistic. In other words, how many standard errors is our hypothesized value from our sample values, which is, our standardized test statistic is statistic minus parameter over standard deviation of the statistic. Well, now the standard deviation of the statistic is down here, just like we did with an interval. It's that thing. It's that messy looking thing. Okay, the statistic, well, we got two of them, and we're subtracting them. So we subtract our 2x bars. Our parameters are these two things. So we'll subtract those. So if we did that right quick, we would say, okay, z, our statistic is just going to be x bar sub boy minus x bar sub girl, okay? And then we're going to say minus our parameter, which is going to be, that's not x bar, it's p hat. Why do I keep doing that? It's p. I'm so sorry that I do that, because that is a bad mistake to make. It's p hat. So I just worked out all the Section 2 problems, so I've been writing x bar for the past hour, and so I'm sorry. But anyway, all right, so, so the difference in our parameter is p sub b minus p sub g. But the thing about it is, p sub b minus p sub g is, if the null hypothesis is true, that's going to be 0. And we're doing this whole reasoning, just like in Chapter 9, our whole reasoning here is we're going to assume throughout this whole test that the null is true. And the premise of this, if the null is true, what's the probability we're going to get sample values this different? And find that probability, and that's a p-value. All right, but since we're assuming the null is true at this point, this would be 0. So in essence, our numerator just becomes the difference in our p hat sub b and p hat sub g. Okay, over our standard error, just as it, this. All right, the next concept is this. Because P sub B and P sub G are the same, theoretically, the way we're doing our test, we are going to come up with what is known as a pooled P hat. A pooled P hat is, in essence, the average of these things, sort of. Okay? And to get your pooled P hat, what you would do is you're going to take your total number of successes, which is 56 in the first sample plus 45 in the second sample, over our two sample sizes, like that. And so we're going to pool them together, and so that is going to be 101 over 200, and so that is 0.505. Okay? Now, the thing about it is, if we assume that our two population values are the same, like the null said, a better estimate would be for our proportion would just be to average those two, since theoretically at this point they're coming from sort of the same population. And so this is going to be a better average in essence for us to use. And so our formula would thus, we would use that in our formula as opposed to those values. And so this would become the square root of, and so as opposed to 0.56 and 0.45, we're going to use 0.505. And so this would be 0.505 times 0.495 over 100 for the boys. And then for the girls, 0.505 times 0.495 over 100. That would be our standard error here. And so anyway, when you do that, and of course this number right here, that's going to be 0.56 minus 0.45. And then when you do that, our z-test statistic ends up being 1.5557, okay? Now, what that is telling us, it's telling us that's how far apart these things are in standard errors. And you remember, like in a normal curve, well, if you're like one, standard deviation, one and 1/2, that's not that unusual. What's really unusual, if you're looking at our sampling distribution here of our differences, so in essence, here's 0 standard deviations. Here's 1 right at this inflection point halfway down the hill. 1.5's like right here. That is not that unusual. Once you get to like this is 1.557. So once you get out here to 2 or 3, it starts being really unusual, and you'd say, whoa, these things are really different. But that is sort of intuitively telling us they are not that different. Of course, the p-value is going to give us a more exact value. Now, how can I find this area that's on the outside here, which this is a two-sided test, so it would include this area, negative 1.5557 as well, since it's two-sided. But before I do that with normal CDF, and I realize this is really complicated looking, but the good news is this, is you can just use the shortcut on your calculator to find your test statistic p-value. And you say, well, why didn't you just show me that at the beginning? Well, because you need to be able to go through this, and you need to be able to kind of understand, the details here. I mean, being able to do the shortcut is good, and that's all that's really required, but you could be asked about something like this, even though it's not considered a major issue. So here we go. So we are going to go to, let me clear this, we're going to hit the stat button, and we're going to go to tests, and we are doing a 2-proportion z-test. There it is. The 2-proportion z-test is the next thing, the 6th option. So when I do that, now it went ahead and entered those values since I did the interval. So 56 out of 100, 45 out of 100, and our alternative is not equal to, once again, these have to be integers, and your x's have to be smaller than your n's, which, by the way, and I meant to mention this as well, it's not critical that your sample sizes be the same size. That really kind of doesn't matter. Most of the time they're not. It's just in this particular problem they are. All right, so we go calculate, and so there it is. There's my test statistic. There's my p-value, so let me go ahead and write that down. So my p-value is equal to 0.1198 approximately. That's the big number we're really going for. And, make sure and write it as p-value. Don't write p. P is a different thing to us, a population portion. Notice the p-hat. So that p-hat sub 1, that's my first sample value. P-hat sub 2 is my second sample value. And then there's the pooled p-hat, or the book puts a little c by this for p-hat combined, of the two. And so that only occurs during testing. It doesn't occur with an interval. So that is the pooled p-hat that is in essence used. So anyway, okay. And so there is my p-value. So now your p-value statement, the p-value statement that we're going to the conclusion is just like last chapter. So hopefully you're getting good at saying our 3 little statements here. This p-value, and you say what it is, 0.1198, is greater than our alpha. And once again, alpha is not set in this problem, so we're using 0.05. But alpha is just the value that if your p-value is below that value, you reject the null. If it's above that value, you fail to reject. Or technically, less than or greater than or equal to, you fail, reject. But anyway, this p-value is greater than 0.05. Thus, I fail to reject. We never accept, fail to reject the null hypothesis. And then what we're going to say is we are going to say, thus, I do not have convincing evidence that, and then at this point, you're going to restate the alternative in context, okay? You're going to restate this thing in context, saying what those things are, okay? So that's what I'm going to do. So I have convincing evidence that the proportion of boys who like this school's lunch is not equal to the proportion of girls who like this school's lunch. Now, you may say to yourself, why in the world did I have to define P sub B and P sub G twice? Because you have to do it there and you have to do it there. And I don't like it either. And I've complained about it, and no one says anything. I mean, there's other people, no one with any power. But they're real big on making sure to draw your conclusion in context, but also making sure to define what any variables you have here. So it's just what we have to do. And, I guess things could be worse, but that's how you do it. Now, by the way, so using, without using that shortcut on your calculator, using normal CDF to find this p-value, or you could use your table, in essence, to find your p-value. So let me show you how to use normal CDF to find that. So to use normal CDF to find a p-value, you go second distribution, and then you go to, what am I doing? Second distribution, go to normal CDF, and I'm going so I go 1.5557 to infinity, 1 EE99, and then mean of 0, standard deviation 1. I standardize this value, so I use the standard normal curve. And it'll automatically give it to you, actually. And so you go like this, and you go like that. And so that would be one tail of it. But since it's a two-sided test, it's not just this big or bigger, it's this different. So you have to include the tail on the left as well, which is going to be the exact same size. So you go time 2, and so there's our p-value. So that is in essence doing that by hand. Or you could use your table, your Z table. So let me remind you in regards to that. So you would go to 1.56. So I'll go to, on my table A, go to 1 point. Now, and the thing about it is, it's always giving me the area to the left of my Z-score, okay? And so I'll have to use this one. So negative 1.56, or to the left of that. So that's going to be on this other page. So I go here to negative 1.56, negative 1.5, and go over to the 06 column. And so that is that. And so that would be that tail, there. And so you would just multiply that number by 2, and that gives you an approximation of the p-value. But lastly, in section 10.1, I'm actually going to post another example of an experimental design problem. But number 3, this is a very important issue. So, and we did this last chapter, and we're going to do it this chapter, and we're going to do it in chapter 12 as well. We won't do it in chapter 11 because there's no intervals with chi-squared. But anyway, so it's important that you're able to make the connection between the null hypothesis, the p-value, and the confidence interval. Remember, okay, so our null hypothesis is that there is no difference. P, and I'll just write it like this, P sub B minus P sub G is equal to 0. That's our null hypothesis. There's no difference. All right, so our interval that we got is negative 0.0277 to 0.2477. That is, in essence, the plausible values for this difference. That is the plausible values for P sub B minus P sub G. Okay, and then our p-value was high. It was 0.1198. That is our 95% confidence interval, 95% confidence. And we would say this, notice the hypothesized value is in the interval. Therefore, it is a plausible value and would generate a high p-value, which this did. How high? Above the related alpha 0.05. These things have to add up to 100%, 95% and 5%. So we would say this. We would say 0 is in the 95% confidence interval and is thus a plausible value for the difference in our parameters, P sub B minus P sub G, and should not be rejected. Should not be rejected. And then the connection with the p-value, which is greater than 0.05, also tells us to not reject the null hypothesis. And so that's our connection, and that's it. Okay? And I appreciate you watching this video. You have earned a smiley face star. So congratulations. I wish you much success. I hope you think about this and read your book and pay attention in class and so forth, and talk to your classmates. Maybe watch the Khan Academy videos. They've got other things on this that give a little bit of a different twist on things that can help deepen in your understanding. But thanks again for watching, and I'll have, like I said, I'll have one more video that is a very similar thing about 10.1, and of course I'll post the 10.2 video. So there you go.